Well, thank you, Georgia. So what I'm going to do first is just give sort of an overview of El Nino and then sort of show you how our presentation is actually going to be outlined, and then I'll pass it off to each prospective person. So overall, what the side event will talk about is El Nino, what it is, why it's important, what are its impacts, and specifically, how does it impact you? How does it impact you on the local, on the regional, and also on the basin scale perspective? The reason why we have the presentation sort of following this geographic order from local to regional to the basin scale is really due to the fact that it illustrates the evolution of our scientific understanding of ENSO, basically starting out as an observed phenomenon off the coast of South America here in Peru, to a regional in situ observations and forecasting across the Equatorial Pacific, then to sort of a basin and global scale perspective from satellites itself. So I will be giving this over to Francisco in a second. He'll be talking about the local perspective. Ken will be talking about the regional perspective, and I will be talking about the basin perspective. So with that, we go to the next. Hopefully you all have heard of El Nino. El Nino itself has been a well-publicized and highly accepted phenomenon within the media, from newspapers to local and also national television stations. You may have seen or heard statements such as these, but you still may not really have an understanding on what El Nino is, what are its impacts, and really why is it important. On the importance factor, we're going to, again, get into that with regards to those different geographical regions, but overall, El Nino is a coupled ocean atmosphere phenomena that has global implications. It has that through two ways, one being weather patterns, as you see here in the top image. Basically, El Nino is associated with extreme drought or extreme precipitation throughout different regions of the globe. Also, in the bottom left-hand side that you see here, it's associated with different hurricane intensity, if you will. Basically, in the northern hemisphere here in the Atlantic, you get less hurricane activity, but in the eastern Pacific, you get more hurricane activity going on. And then in the lower right-hand side, you just see overall, ENSO actually interacts with other climate processes. You have the Pacific Decadal Oscillation, the North Atlantic Oscillation, et cetera. So that's one way it's important globally, weather patterns. The other being it impacts the global food market. So typically when an El Nino occurs, it's been associated with a collapse of pelagic fisheries off the coast of Peru, specifically anchovies, as you see in the top left image. Also the reproductive failure and mortality of seabirds, as you see in the bottom left-hand side. These are dead pelicans off the coast of South America. Also, it's been linked to or contributes to a decrease or mortality of coral reefs. So that bottom right-hand image that you see, the 1997-98 El Nino is potentially linked to about a 20% mortality of corals globally. So overall, all these things themselves are very important, but you're probably saying, why does that relate to the global food market? Well, if you look on the upper right-hand portion there, the left-hand side that you have here actually is the top fish meal and oil producers. Peru is number one. If you look on the left-hand side of that image, it shows the top sort of consumers of that fish oil, the fish meal and oil, and the top being the Asian countries. So you can imagine if you have a collapse of pelagic fisheries, clearly that's going to impact those consumers, and it will translate to other food staples, potentially coffee, chocolate, soybeans, potentially. So overall, again, El Nino is a globally important phenomenon. It has global implications. But we really want to talk to you more so from these different perspectives, first focusing on the local perspective, then the regional, again, then the basin. So with that, I'm going to pass it over to Francisco Chavez, who will now talk about the local perspective.
Thank you, Michelle. So I'll start here with is to give the local Peruvian perspective for El Nino, and I have a couple of things on this slide. One is one of the first papers ever written about El Nino by a man called Iguiguren, who talked about the rains in Piura, and he was one of the first ones to put together the fact that the ocean warmed with this meteorological phenomena. The other one at the bottom, which is a little bit of a tongue-in-cheek paper that I wrote, it's called the legitimate El Nino current, and I'll argue that there is a little bit of an El Nino legitimate current in northern Peru, but of course now we know of it as this huge global phenomena. So a little bit about the history of El Nino. It was coined in the late 1990s by fishermen in northern Peru who observed a warm southerly current around Christmas time. Hence the word El Nino. It's the capital E, capital N, which is the Christ associated with the Christ child. unusually warm years associated with extreme rainfall in Piura, and the appearance sometimes of crocodiles that were found in the tropical regions in northern Peru and in Ecuador. Another piece of trivia, the ENSO is associated with a phenomena called the Southern Oscillation. And it was in the early 1920s that Sir Gerbert Walker coined the term by stating that when the pressure was high in the Eastern Pacific, it tended to be low in the Indian Ocean. And it wasn't really until the 1960s that these two things were linked, that this, what we thought was a very small warm current in northern Peru and this very large change in atmospheric pressure globally were linked. And we now refer to this phenomena as ENSO. Peru is we're here in Lima at the COP20, and Peru is probably by far the country that's most affected by El Nino. The little town on the left, I was born actually up here in a little town called Talara, and I came back to study the local oceanography in a little place called Paita, and it was there that actually the birthplace of El Nino, the fishermen from that area, and that both of those cities lie in the state of Piura, which is the state that's probably most affected meteorologically by El Nino. When I first came to start my work in Paita, on the left hand I found the picture of the top left, a desert with these small streams that run through there. When I returned there in the middle of the 82-83 El Nino, that area had become a grassland. There was frogs, deer, ducks that had come down from the areas. So this area obviously feels these rainfall events occasionally, and it turns into an unusual place. If you were to go to the Galapagos Islands, and then the bottom left, on the bottom panels, the picture on the left was taken during a cold year, and the one on the right, and you could see the difference in the vegetation in those two locations. This is what happens with sea surface temperature during an El Nino event. This happens to be for the El Nino of 82, 83, 84. The dashed black line is the average year, which tends to be warmest in the Peruvian summer of January, February, March. The blue line was the temperature that was measured in Paita during 82, 83. And in May of 1983, the normal temperature in Paita, which was around 20 degrees, was about 30 degrees C. There is no place else in the world where we feel anomalies of this size. 10 degrees C is a huge change in the ocean, and it's associated with these huge changes in rainfall and other consequences. And I say that the 82-83 El Nino changed my life. I wasn't planning to become a student of El Nino, but nature forced my hand. The other thing, many things changed during El Nino, and one of them is the height of the sea level. When I first came to start the time series in Paita, Hector Soldi, which was then Lieutenant Soldi, now retired Admiral Soldi, and I went up the coast of Peru to find a place where we would start a set of observations. Hector was installing sea level gauges, which are a very good tracker of the El Nino event. In fact, again, if you look at the dashed line as the mean, you can see that during El Nino events, sea level in the coast of northern Peru increases by an order of 40 centimeters or so. In fact, normally, sea level in Ecuador and northern Peru is about 40 centimeters lower than it is in Indonesia. And during these big El Nino events, there is this redistribution of water from one side of the Pacific to the other. And this increase in sea level actually drives this, what was considered the small warm current in northern Peru that the fishermen called El Nino. There are changes in circulation, but the biggest change hydrographically is in the depth of the thermocline. And this is, sorry about the technical term, the thermocline is the place where the upper layer of warm water changes rapidly to the layer of cold water. So the thermocline is the area of rapid change. It separates the warm, nutrient-poor water of the surface with the cold, nutrient-rich water below it. And it's from that cold, nutrient-rich water that upwelling recruits nutrients. And this little diagram kind of tells you that, shows you that, with the water being recruited from below the thermocline, leading to blooms in small plants, which then lead to a very happy fisherman. During the El Nino periods, the thermocline deepens, and the water that's recruited is no longer rich in nutrition, and the ocean becomes more like a desert. The NASA satellites have allowed us to see these effects from above. And this example is, and Michelle mentioned this, I think, earlier, that many of our satellites just started in the late 90s, but this image shows you how the 97, 98 El Nino, the purple colors are low concentrations, and the red ones are high, and you can see how different the 97, 98 condition was with the other years. And the entire fauna of the Peruvian waters changes during these events. The typical dominating organism, the anchovy, becomes scarce, comes close to the coast, or migrates southward, and tropical species like mahi-mahi enter. Shrimp become prevalent from areas that are typically to the north, and they come down to the south. So the entire ocean of Peru changes during these events. During my PhD work, we found a very close correlation between these warm events, which in the case of the top line, I've inverted the temperature scale, and you see that when the times that the ocean gets warmer, the catch of anchovy off Peru goes down. And today, we have somewhat of a small El Nino or medium El Nino going on here, but what we didn't know back then was that there are also these changes that happen from decade to decade. And this time series of the catch of anchovy and sardine shows that during some decades the anchovy proliferates, and in some decades the sardine does. And the decline that we've seen recently off Peru may give us an indication that something is changing. And this link, this local link, then these changes that happen here along the coast of Peru are linked to what I call large-scale, regional-scale changes in thermal dynamics, where the normal cool condition that's seen along the coast of Peru and along the Equatorial Pacific disappears. The normal is in the bottom panel. The El Nino condition is in the top. And those changes are associated with changes in productivity as well. So with that, I'm going to hand it over to Ken to take on the regional perspective.
Thank you, Francisco. So now I'll be talking a little more about the large-scale processes. And Francisco already mentioned some of the key time series that were initiated with the 82 El Nino, which was one of the biggest ever seen. But that event, in itself, it triggered a lot of activity on ENSO research and also in observations. And one of the key results out of that was the establishment of a very comprehensive observation network in the tropical Pacific. And this was mainly framed around the TOGA program. So this diagram here summarizes some of the key elements of that observing system. So we have, for instance, satellite observations on the top. Michelle is going to talk more about these later. But there's also a variety of different ocean platforms from which measurements have been taken for a long time already. So we have perhaps the key component of this observing system is the Tau Triton array in the Equatorial Pacific. So this is an array of buoys, of moorings, measuring a variety of meteorological observations at the surface, but also subsurface ocean properties such as temperature, salinity, and others. So out of this information from which we have long and continuous time series in many cases, the scientific community has built a conceptual understanding of the mechanisms behind El Nino, which has enabled us to have much better predictive capability. So perhaps many of you have already seen these cartoons. First of all, this is what we would consider the normal conditions in the tropical Pacific. So this diagram is showing us the surface of the ocean with colors. That would be the surface temperature. And below that, we have the thermocline, which Francisco already mentioned, which is the boundary between the warm surface, near surface waters and the deeper cold waters. Sorry about that. But that distribution, I mean, the surface temperature has warm conditions on the west and cold conditions on the east, and a thermocline that's shallow in the east and deep on the west, are both a result and also a forcing of the wind that are blowing normally from east to west, pushing the warm waters towards the west and raising the thermocline in the east. Now, these winds are not totally independent from the ocean because as you can see in the diagram, over the warmest waters, we also have strong convection, strong rainfall. And those storms are actually an engine that drives the circulation of the atmosphere. So where you have the warm water and you have the strong rainfall and convective processes, you have upward motion, and that air comes back towards the east on upper levels and then sinks on the eastern Pacific and completes the circle. So that circulation cell is known as the Walker circulation. And that circulation depends on what the ocean conditions are. So we have on one hand that the ocean is driving, the ocean is driving the atmospheric circulation, but also we have that the atmospheric circulation is driving the ocean conditions. So that two-way interaction between those two is essential for the dynamics of El Nino. And that's something that has been really consolidated thanks to all these observations and through all the research that's been done in the last, say, 30 years. So during El Nino, this changes. We have we could begin anywhere in this plot, but let's just start by saying that if the warm waters were displaced to the east, say on the surface, that means that the rainfall and the convective systems would also be displaced to the east, or Central Pacific in this case. The winds would also respond to this. They will weaken on the western side, and maybe even reversing, so that the wind are now pushing towards the east. And the thermocline deepens on the eastern side as a result of that. And that in turn drives further warming on the surface. So that reinforces the initial warm anomalies that I mentioned. And you could start this argument anywhere around that circle. So what we're talking about here is about a positive feedback loop by which we could perturb the system anyway, and then we have all these interactions amplifying that. And that can lead us from normal conditions to El Nino. So this is kind of like our conceptual model as a result of TOGA and the Tau Triton array. Now, new questions are emerging. Oh, sorry, before that. This is the kind of observations we've been using to build, to really give support to this conceptual model. This is actually Tau Triton data. This is I can explain. This is time going from up to down, and it's longitude going from west to east. And these are three different variables. We have westerly winds, we have the sea surface temperature, and then we have the thermocline depth on the right. So what we can see here is, for instance, in the westerly wind bursts, we can see in red that this would be anomalies of winds pushing from west to east that would drive on the right-hand panel. We have these eastward propagating pulses in the deepening of the thermocline, which we know to be Kelvin waves. And these Kelvin waves, in turn, drive some of the warming on the surface. And the processes by which we have the warming actually we can at least identify three different ways. One would be due to the deepening of thermocline, we have a reduced cold upwelling, which Francisco mentioned already is key for the coastal ecosystem in Peru. We also have warming by zonal advection, which means that just only that the winds are actually pushing the warm water to the east. But we also have that the winds by themselves are cooling the surface of the ocean just the same way in which we can cool our cup of coffee by blowing on it. So these basic processes we already understand and form our basic conceptual model of how El Niño works. And now, as I mentioned earlier, now we have new questions, and these are emerging from now considering different types of El Niño. So we have a conceptual idea, a conceptual model of how El Niño in general works, but now we're starting to focus as a community more on the differences between events. And one of the most dominated type of El Niño in the last few, say 15 years, has been a different type in which instead of having the warming to be strongest on the east, on the Eastern Pacific, now we have a warming on the Central Pacific. So these are roughly two different types of El Niño. I mean, they're mainly differing in the pattern, but as I will show in a few minutes, moments, the pattern matters a lot, particularly if we're looking at the impacts elsewhere in the world. For instance, if we look at the impacts in terms of the effects of El Niño on the rainfall anomalies on Peru, we would have, if we look at the left-hand panel, we have that the warming of the surface on the Eastern Pacific will lead to more rainfall along the coast. And this is something Francisco already mentioned. Now, perhaps an intuitive result is that if we have warming not in the Eastern Pacific, but in the Central Pacific, then the anomalies we get are actually less rainfall, but not so much on the coast, but more on the mountain side of Peru. So we have that El Niño can have two opposite effects on Peru. And the reason is that one is the local effect, just the warming of the coast of Peru leads to moister air, warmer air that leads to more rainfall directly. That's a local effect. And then we also have a remote effect from the Central Pacific towards Peru that leads to reduced rainfall. And this remote effect is what makes El Niño be important for not just for Peru, but for many countries around the world. And for example, like here we have two different type of effects now in the US. This would be for the autumn months in the US, for the Eastern Pacific type of El Niño, and for the Central Pacific type of El Niño, in both temperature and precipitation. And these are both now remote effects, what we call teleconnections. We can see that the impacts are very different depending on where the warming takes place in the ocean. So again, the pattern where the warming takes place is key for understanding or predicting the impacts. Now, in terms of forecast, our main tool right now is numerical climate models. And these are just computational tools fed by observational data, which we run to get an idea of what's going to be the future of the climate in the next few months. And the models have become very good, but still there's some aspects of that of the predictions that are not as good as we would like to. For instance, here are some predictions for the next few months for the coastal region of Peru. And these are for the next few months. But now on the bottom panel, we have what the forecasts were for the last 30 years. So beginning in '82 towards almost the present, we have in the red curve what actually was measured, and the black curve, the forecasts. And we can see that in general, for the very extreme El Niños in 97, 98, and 82, 83, we had that the model predicted El Niño, but the amplitude was around half. And on the other hand, if we look at the 2010 event, which was also almost a strong event in the Central Pacific, so no warming along the coast of Peru. So you can see that in the red, almost flat line. The model actually forecasted a strong El Niño. So even though the model is able to predict whether El Niño is taking place, it's not able to distinguish between whether it should be having warming in the east or not. So these are new challenges that models have to deal with. And there's a variety of problems with the models that we already know of. I mean, these are old errors in the models. And the problem is that we still haven't been able to figure out how to fix them. So this is still work that we have to keep going. And just to give you an idea, the bottom panel on the right is just showing the mean error in the surface temperature. And it's almost over 2 degrees C off the coast of Peru. And this is a very old error, and we still haven't been able to fix, although some advances have been made. This is just to show some of the physical processes we're, as a scientist, starting to look at to understand why or how the models are getting things wrong in the Eastern Pacific. And so these are new questions. This is new science we have to do in order to move forward. And well, we're now at the Climate Change Conference, so I'll just say a few words about climate change now. This is from the IPCC report, the latest report of 2013. And there hasn't been many changes relative to the previous report. It's saying that ENSO in climate models has improved, so their models are better in that. The report is saying that the ENSO is going to continue being the largest source of variability, climate variability. I'll jump to the last one. Because El Niño changes naturally, substantially, we're not able to say whether any changes we've seen in the past are due to climate change or are natural. And on the other hand, if we look forward to the future climate with the climate models, there is really no consensus on what the changes are going to be, whether the Niño is going to be more frequent, is it going to be stronger or weaker or less frequent. So the lack of consensus at this point just means we don't know enough. One thing that this report is saying now is that because of the increased moisture in the atmosphere, because of the warming, the rainfall events associated with El Niño might be stronger than in the past. So that's something we could use, even though we don't know whether El Niño variability itself is going to change. Now, there's still a lot of work we have to do here, and part of that involves more research, more understanding, but also new kinds of measurements, new type of information. And with that, I'll just lead to Michelle's talk.
So I have to see this. Sorry for the noise, but we asked the Peruvians to give us an ENSO soundtrack, so that's sort of what's going on in the background. But with regards to that, so building upon what Ken was talking about, so in addition to in situ sort of measurements that we have across the Equatorial Pacific, satellites have been an additional sort of key implementer, if you will, in our understanding of El Niño and its spatial and temporal evolution. So it's really the coupling of the two, the coupling of in situ and satellite that really provides the full context of ENSO and what it's doing, what its processes are, what its impacts. In situ provides us with a surface and subsurface. Satellite provides us with a much larger spatial view and temporal coverage. So again, it's really the two, the linkage between the surface and subsurface that is really key. But I'll only be talking about more so the satellite. So since about the 1980s to 1990s, as Francisco mentioned, there have been numerous satellite observations or satellite sensors that have observed aspects of El Niño. So from, let's say, precipitation measurements from TRIM, as you have here on the bottom, to its predecessor that we currently have, GPM, which is on the top, it's recently launched, to ocean vector winds from QuickScat, to its predecessor, RapidScat, also recently launched, that's on the top, to also sea level rise, or sea level in general, from the altimeter series, to also SST measurements that we have from satellites like Aqua and Terra. All of these have really contributed to our understanding and assessment of El Niño and its variability. So just to give you an example of that, shown here are some different satellite observations sort of merged together to provide an El Niño sort of simulation. Again, it's real data. So what you're seeing, in fact, here, the background color is sea surface temperature anomalies. So the red indicates temperatures above normal, blue temperatures below normal. Normal here is just an average temperature over a respective period. So the vectors that you see are, in fact, ocean vector wind anomalies, and the wiggle that you see in the elevation is sea level anomalies. So overall, everything that you're seeing here is exactly what Ken portrayed in that El Niño cartoon that he showed. So basically, before El Niño begins, you get a relaxation of the easterly trade winds, which you do see when it starts up again. You start getting westerly wind bursts from the western tropical Pacific, and with that, it basically moves or displaces that western Pacific warm pool water eastward. In association with that, you're also at the same time in the Eastern Pacific, as Francisco mentioned, and thank you for explaining the thermocline, it actually depresses the thermocline. So you get warmer water occurring deeper within the water column itself. So overall, the contributed effect is that sort of doming of that warm water all sort of being sort of piled on one side in the Eastern Pacific. So this is ENSO. This is what we can see from satellite observations. It's providing us with a more global spatial view and temporal sort of understanding. But again, we really can't get at that subsurface, and that's why we really need the in situ measurements. So aside from the physics, we can also say something about the biology from satellites. So the biological response to El Nino. So this is chlorophyll concentrations from ocean color instruments such as NASA's SeaWift satellite. And what basically you're seeing here is chlorophyll. Chlorophyll is a proxy for phytoplankton biomass. So phytoplankton represent the lowest trophic level in a food chain. So if you think about they're at the base, basically any changes in them will have a bottom-up effect on higher trophic levels. So if you think about it, it goes, let's say, phytoplankton to fish, fish to us. So clearly it does impact us in that manner. And right now we can only see phytoplankton from space, not fish, maybe one day. But with regards to this, overall, when you have El Nino, when you also get that depression of the thermocline in the Eastern Pacific, you're also depressing the nutricline, which, as Francisco was talking about with temperature, it's basically the change in a highly nutrient-rich region to a highly nutrient-poor region. So overall, there's less nutrients in the water column, so less nutrients for that phytoplankton to grow off of. So this illustration hopefully demonstrates that point. So on the top image is during El Nino, the bottom is during a normal year. So overall, the normal year, you see enhanced chlorophyll concentrations or biological activity all the way from the coast of South America, Peru, out towards the Equatorial Pacific, where in the El Nino period, the top image, you can clearly see that there's a stark contrast. You're getting a reduction overall in chlorophyll. So clearly that would have implications upon the higher trophic levels in us. So I talked about physics, I talked about biology, now the atmosphere. So what can we see from satellites in the atmosphere? So when I was mentioning those sort of global implications, I mentioned weather patterns. So shown here is rainfall anomalies from TRMM. So the red indicates higher precipitation, blue reduced precipitation. So typically in a normal year, as Ken's cartoon pointed out, you basically have over Indonesia and Australia a lot more precipitation during a normal year. During El Nino, that precipitation or convection band shifts eastward. So what you're seeing here then is a shift. So you're getting reduced precipitation occurring over Indonesia and Australia, or a drought, and you're actually getting enhanced precip occurring more so towards South America. So we can see this, and more so importantly, not only look at individual measurements, we can also from satellites sort of merge them and look at this complete view. How is the physics and the biology and the atmosphere all responding together and really impacting our system? So we can do that, but we can also look at how El Nino is varying in time. So as Ken pointed out, there's been talk of two different types of El Nino, or just El Nino variations in general. And all that means is basically the sort of placement of warming has sort of shifted. So the top two plots are sea surface temperature anomaly, again, just temperatures above normal, where the bottom is sea surface height anomaly. And overall, on the left-hand side is the Central Pacific El Nino, right-hand side Eastern Pacific. So you can see between the two for both plots that, again, it's just sort of the placement of that warming or that sea level rise that's different between the two. But we can look at this from a sort of spatial view and analyze it in time. But we can also look at trends. So this is a recent study by Lee and McFadden in 2010, and they basically wanted to look at the trend of increasing El Nino intensity in the two different regions, Central Pacific and Eastern Pacific, over the last 3 decades of the satellite sea surface temperature record. So on the y-axis, you have El Nino intensity, the x-axis year. Those red bars indicate the Eastern Pacific El Nino, the pink Central Pacific El Nino. And again, on the left-hand side is the Central Pacific Basin, right-hand side Eastern Pacific Basin, and that red dashed line is a trend. So hopefully looking at these plots, what you should see is that the trend basically in the Central Pacific is you're getting an increasing intensity in El Ninos occurring in the Central Pacific, and the opposite is true in the Eastern Pacific. We're getting less El Ninos, less intense El Ninos. So if such a trend continues, if we're just going to see more Central Pacific El Ninos occurring, what impact does that have upon oceanic and atmospheric processes, and how does that translate into economic on local, regional, and also basin and global scales? So for that to happen, again, understanding El Nino in its current state, looking at its variations, and going the next step, we really need to have sustained measurements from satellite and sustained measurements from in situ. Again, it's the coupling between the two that really provides us that total view of El Nino. But as you can see in the bottom here, so this is just illustrating the recent vulnerability of the Tau Triton array that Ken was mentioning that's been so pivotal in us understanding the sort of subsurface dynamics of El Nino. As you can see sort of in this plot over here, this illustrates over time sort of the percentage of data return and the percentage of the number of buoys that have actually provided data. And you can see there's a rapid drop-off. It's starting to increase, but over time there has been some vulnerability that we've experienced. So again, sustaining those measurements is really key, but also going beyond. So this is about the Tropical Pacific Observing System 2020 project that myself, Francisco, and Ken are all part of. Ken's actually on the steering committee. And basically the point of this was there were a lot of activities that were going on. They were loosely coordinated, and we were doing some measurements here and there, but it's really to sort of bring together those communities, but also to assess what do we need to do to really sustain those measurements. So that's what this is about, sustaining measurements, sadly in situ, but also adding new perspectives, new measurements. It's wonderful that we have what we have, but always, as scientists, we want more. We want to understand the entire system. So for this, we actually added a biogeochemistry component to the sort of Tau Titan array, thinking about that perspective. How do these different sort of chlorophyll increases, decreases impact the carbon cycle? So looking at it from a biospherical, atmosphere, ocean, carbon cycle, if you will. So if you guys have any questions with regards to the TPOS 2020, we can ask that afterwards. But so with regards to that, echoing the same sentiments, sustaining measurements, going to the next step, the next generation, NASA's doing that as well. So we are continuing our observations, but we're also looking at new observations. And I'll just call out a few. And these are for global. It's not just for El Nino, global, any process that you can possibly think about. I'm just sort of going to reference it in terms of El Nino. So you have SMAP on the bottom, left-hand side. SMAP is it's going to give us soil moisture. So if you think about El Nino, I talked about extreme droughts, extreme rainfall. You can then look at maybe the terrestrial component to that. How is it really impacting? That's something that SMAP could provide. You also have SWOT. SWOT is the next generation ocean altimeter that we have. So it's going to be ultra high resolution spatial. So you could think maybe you could see subscale, sub-mesoscale features, filaments, see how that actually interacts with El Nino. But also, this satellite's going to provide us hydrology. So that's another key component that'd be very interesting to assess. And near and dear to my heart is PACE. So PACE is the next generation ocean color instrument. So when I talked about biology, I talked about chlorophyll A only. Chlorophyll A, there's a lot of different components. I mentioned it was a proxy. It's not specifically phytoplankton biomass. And phytoplankton, you're lumping together a bunch of groups. Each one of those groups have a different impact upon the carbon cycle. So PACE provides the opportunity potentially to look at phytoplankton species discrimination. So we can actually see which species takes over when El Nino happens, when then link it to the carbon cycle, if you will. So overall, I hope at the end of this presentation, which is going to be now, that you've learned a little bit something about El Nino, you've seen why it's important, you see what its impacts are and how it might relate to you all, but also too, you see the inherent need for these sustained measurements, both satellite and in situ. So with that, I'd like to say thank you, and then I think we're going to open up to questions where we're all going to be here as a panel review. So thank you.
Thanks so much, Michelle. So I'd like to invite all the panelists to come up to the front. And we'll definitely take some questions from the audience. Does anyone have anything right now? Questions for, okay, in the back? They may have. So if you could just say your name and your
My name is Itabutu from Ethiopia. This was really excellent presentation by a group of scientists. I wonder whether this El Nino has a global impact. We were talking about its impact on Peru and its region, the Pacific countries. How about, for example, Africa, East Africa? Does it have any impact on those regions?
Thank you.
Yeah, in a paper that was published with the paper that I showed, Rasmussen and Wallace showed that the rainfall in Africa was tightly coupled to El Nino events. Changes in material dropping to the bottom of African lakes or in lakes in the Soviet Union are associated with El Nino events. So El Nino is truly a global phenomena and affects everybody. And the better we can forecast it, the better the climate in any part of the world could be. Our next challenge is how to get these decadal changes, because as was mentioned by two of the speakers, the Central Pacific El Nino has a different response on climate than the eastern one. So that's our, and they seem to change on a decade to decade basis. So for 20 years we may be doing one thing, and for 20 years we may be doing other. So that's the next challenge for the forecasters. I don't know if anybody else has any comments on that.
Thank you. Any other questions? Sure.
Yes, sure. Thank you very much. Excellent presentations, very informative technically. My name is Amir Delju from World Meteorological Organization. Our organization is the only UN body that provides consensus El Nino updates every 3 months based on the output of global models. My question is that what is the main reason for disagreement among the output of global models? We know that there is some degree of differences on the outputs for El Nino forecast. What is the main reason? This is the question. And piece of information, I should inform you that WMO will have a side event on 4 December, 1 to 2:45 in room Machu Picchu, Thursday, 4 December, on El Nino technical briefing. This is a joint side event organized with FAO and CFEN. So anybody who is interested on this subject can participate. Thank you.
I'll give that a start. I think it's mainly because the atmosphere is somewhat chaotic. And so once we know what the atmosphere is doing, the models behave, the ocean models behave very well. But it's the feedback loop to the atmosphere that we don't quite understand very well because of the short-term chaotic nature of the atmosphere, which in the end may be one of the reasons why our predictive models may not, have their limitations. But Ken, I think, would probably have other.
Yes, in terms of the argument or consensus among models, I think the issue is not whether they're contradicting each other, but whether they're all wrong in the same way. And the case of what I was showing for the forecasts of the Eastern Pacific, they tend to be wrong in the same way. So they tend to underestimate the variability in the Eastern Pacific. There are long-standing biases in the Eastern Pacific in pretty much all of the climate models. So in that sense, there is a consensus. But that's a problem that we have to, there's not just one model we have to correct. There's pretty much all of them. So it points rather to a deficiency in a particular model to a limitation in our, that's my music, I guess. No, it's a limitation in our understanding of what the processes are that are relevant for a particular region like the Eastern Pacific, which pretty much no model gets right. So, and that's something we have to keep in mind, because both for climate change projections and for forecasts, we tend to think in terms of ensembles of runs and think of their spread as a measure of uncertainty. But if they're all biased in the same way, then that spread doesn't really inform us about the uncertainty. We have to keep in mind that there's structural problems in terms of the uncertainty.
Maybe just a very simple answer for your comment is that, for instance, if you take the models that have been developed in the IPCC group, they come from different labs in the world, and these different labs, they have a history of their model, and their model have been developed initially to focus on their regional climate. So some models have different parameterizations and are better suited to study different regions of the world. But if you take subsets of the models that are the least biased in the Pacific Ocean, well, you have some kind of convergence at some, maybe not for the forecast short range, but for the climate change, there are also some recent papers that show that there is better convergence in these models.
Great, thank you so much. I think we have about time for 2 more questions. I see we have a hand here.
Thanks also for the excellent presentation. My name is Matheus. I'm from the African Union Commission. If I correctly followed you, I heard you saying that there is no as such link between climate change and El Nino performance. Probably you were when you talked about the situation happening in the Central Pacific Ocean, if I followed you correctly. So my question is in relation to that. To what extent the predicted climate change will affect the El Nino situation, positively or negatively? That's my question.
So there are some aspects of El Nino in the future that might, we could probably consider robust, in the sense that even if the El Nino variability doesn't change, say if the fluctuations in temperature are the same, if the climate in general is warming, those extremes are going to be hotter or colder, or no, not hotter, just cold, just warmer, warmer than the present. So we don't need to have changes in the variability itself to have more extreme warm events. The same thing happens with heat waves. So even if the variability doesn't change, heat waves you can just be hotter just because the mean climate is warming. Now, in terms of whether the variability of El Nino is going to change and whether the patterns, like I was mentioning, are going to be different in the future, that is much more uncertain. Our scientific understanding of what the processes are, both for the present day differences between the say periods like the last 15 years versus the previous 20 years, we don't really have a handle on that yet, and therefore we don't have a handle of what might happen in the future with the types of El Nino. So the evidence at this point is ambiguous. So the different climate models are saying slightly different answers for the future. So our uncertainty is just too large at this point. We're not saying that there won't be any effect on El Nino from climate change, but we just don't have enough certainty on what they might be.
Great. Would you like to follow up on that question? No? Okay. Great. I think we have another question back here from this gentleman. I think this will be our last question of our event. Thanks, Tori.
¿Puedo hacerlo en español? Ok. Ya. Buenas tardes. Excelente la presentación, muy clara. Soy de Paraguay. Justamente Michelle había mostrado en el mapa de Paraguay la ocurrencia de más impacto de lluvias cuando ocurre en otras latitudes. Este año en Paraguay tuvimos un impacto nuevo y diferente, atípico. No tuvimos invierno y asociado con la salida del fenómeno La Niña al ingreso el anuncio del ingreso del Niño, hemos tenido del Pantanal mucha agua y hemos tenido una inundación tremenda de ciudades y ahora estamos teniendo lluvias torrenciales ya cuando el fenómeno está teniendo activación mayor, de su máxima activación. Mi consulta específica es, ¿tiene alguna relación, siempre hablamos de lluvias, de frío, sequía, ¿tiene alguna relación con los acuíferos, con las napas freáticas? El fenómeno El Niño puede impactar en la salida de más agua, en este caso del Pantanal, donde ocurre este fenómeno.
Should I answer in English or in Spanish? En español. ¿En español o en inglés quieres? What does the English? Okay. So an example I can give you is from where I live in California, where there has been a continuous drought for the last 15 years, partly because of the lack of El Niños. And that has and that has changed the water table substantially. So, and we can now see it with your NASA satellites. The Earth bulges a bit when it has the water tables. Yeah. So, how about if voy a cambiar al español porque hay algunos que no están entendiendo. Cuando se nota la diferencia con los satélites, cuando la tabla de agua está llena o vacía. En el caso de California, la tabla está vacía y se nota. Entonces el inverso es cierto al mismo tiempo. Si tienes exceso de lluvia, se va a llenar la tabla de agua hasta que puede brotar en los pantanos y en esos sitios. O sea que sí puede haber una relación entre la cantidad de lluvia que recibe una zona y las salidas en los pantanos y en ese tipo de cosas. Eso no, o sea, sí es que, pero la lluvia, puede haber habido lluvia en otras partes, porque la tabla de agua está conectada sobre áreas muy grandes, no tiene que llover ahí mismo, puede llover en el Brasil y te puede influenciar a ti en Paraguay. Una anécdota, ya que estamos en esta, que antes que existiera el internet y que todos pudiéramos ver los resultados de las condiciones en la toga Tau, porque ahora todo el mundo puede ver si está caliente o está frío. Me llamaban siempre de Argentina, porque y que está cerca, por supuesto, de Paraguay, porque los cultivos de la soya dependían mucho de que si había niño o niña. Y me llamaban por teléfono porque yo tenía las temperaturas de la costa del Perú y les podía dar, pero me despidieron cuando apareció el internet y la toga Tau.